Hello, welcome back. Let's look at example 3. We're going to get a bit more practice with matrix multiplication here. Let's start with A times B. And maybe we could write out a little bit more of the stuff like we were doing last time. So we know the definition says we're doing A times the first column of B and A times the second column of B to get these two columns of AB. We can write that out like so. Now, each of these results here is going to be a linear combination of the columns of A using the entries in the column of B as weights, like so. So negative 1, 0 gets multiplied by 3, and we add that result to the second column 0, 2, that's getting multiplied by 5. Doing the same thing with the second column of AB, we have 4 scaling the first column of A plus 6 scaling the second column of A. And that gives us a matrix with 2 columns, one that is negative 3, 10, and another that is negative 4, 12. Okay, let's check B times A. Now the definition of this, now that the B is on the left, we're doing B times A1 and B times A2. Like so. And for that, we can just do the 3, 5 column scaled by negative 1, like so, plus the 4, 6 column scaled by 0. And that is now BA1. Let's do B times A2. 3, 5 is scaled by 0. And 4, 6 is scaled by 2. Anyways, it all comes out to be negative 3, negative 5. And on the right, we have 8, 12. So you get this matrix. Now, I've been trying to write this out in a way that illustrates why the row column rule is true. The basic idea is that each one of these entries, like let's say this, I don't know, negative 3, we get that by doing A times B1 and looking at the first entry. And what are we multiplying together to get that negative 3, the first entry in A times B1? Well, we did negative 1 times 3 and 0 times 5 here, right? Or maybe we could highlight this to make it clearer. That is the first entry in A times B1. That is the dot product of row 1 of A, and instead of X, we have B1. Now, the same thing is true in the second entry of AB1, which is this 10 here. We get that by doing the dot product of 0 and 2 with 3 and 5. So 0 times 3 plus 2 times 5 gives you this 10. Likewise, when you're doing A times B2, we're still doing dot products of rows of A with column 2 of B. And that's basically what the row column rule says. The notation might be a little tricky to read, but what it says is that in order to get the IJ entry of AB, that means the entry in row I, column J of AB, then we're going to get the sum of the entries from row I of A, which is what I've highlighted in green. All these are from row I of A, but just column 1, column 2, up through column C, and column J of B. So all these entries you're multiplying by these are from column J of B, but just row 1, row 2, up through row C of B. So the original definition of AB, the one we have over here, it's going to be useful for conceptual understanding, and it's going to be useful for a lot of proofs because we know a lot about linear combinations of columns of A so far. We've been studying linear combinations for most of chapter 1. So it's useful for understanding things. But the row column rule is usually more comfortable for hand calculations. Now, let's just, I think I already kind of did it, but let's just look at the last example, but show how we're using the row column rule. So for AB here, A is -1, 0, 0, 2, and we're multiplying that by 3, 5, 4, 6. So to get the entry in row 1, column 1 of this, we're going to use the dot product of row 1 of A and column 1 of B. So that's -1 times 3 plus 0 times 5. For row 2 of A, column 1 of B, we're going to do 0 times 3 plus 2 times 5. Then for row 1, column 2, we're going to have -1 times 4 plus 0 times 6. And then for column 2, row 2, we use row 2 of A and column 2 of B, like so. And you can see that's basically the same thing I wrote out here, right? So it still gives you -3, 10, -4, 12. Doing it the other way, we're now going to be using the rows of B and the columns of A. Like so. And again, you can see that should be the same thing you get as if you do it either one of these ways that we already did. Yeah, that looks the same. So it should still come out, whoa, it should still come out to be -3, -5, 8, 12. All right, so yeah, let's do a bit more. I think this video we should get up through theorem 2.7 here. But let's look at example 5. Is this true or false? If m times A equals m times B, and m is not 0, then A equals B. Now, this is true with numbers if m and A were numbers, but in this class, capital letters always mean matrices. But with numbers, you could divide them out because you can divide by a non-zero. You would get A equals B, but we can't do that here because matrix division is not really a thing. Well, sort of. Sometimes it's a thing. We'll get to that in the next section or two. But a good way to think about this, to try to think of a counterexample. A counterexample is a list of matrices where the if part is true, but the then part is false. So A is not equal to B. A reason why it's good to try to think of a counterexample is, well, if it turns out the theorem or the statement is false, then and you can think of a counterexample, then you're done. You've proved that it is false. If it turns out the statement is true, you will probably fail to come up with a counterexample. And if you try to come up with a counterexample and fail, then you're learning something about why a counterexample doesn't exist. So let's try to think of how this would work. Maybe we can do 2 by 2 matrices because we have some experience. Let's say that M has entries P, Q, and RS. I don't know. And A has entries C, D, E, F, and B has entries G, H, I, J. Now, we want to make it so MA equals MB. MA, using the row column rule, should be PC plus QE in the 1, 1 position, then RC plus SE in the row 2 column 1 position, the 2, 1 position, and then in the 1, 2 position, PD plus QF, and then in the 2, 2 position, RD plus SF. Now MB should be the same idea, but with the entries from B, like so. Now, if you want to think on your own about how to do this, you might want to pause the video, but I'll go ahead and explain my idea here for how we can make these the same, but make it so the entries in A and B are different somehow. Well, let's say we could make the terms PC and RC respectively equal to PG and RG. And likewise, PD and RD equal to PH and RH. We can do that by making the GH part of B equal to the CD part of A. So those could be equal, but what if we make it so E and F are different, but they get multiplied by 0. So look where the E and F show up here, here, but make that different from the IJ here on the right. We could make it so they don't matter by making it so Q and S are 0. So here's my counterexample. P and R can be anything. Q and S are 0. And these being 0 is going to make it so all the terms that get multiplied by Q and S become 0. And then for A, we can make it so the CD part of A is equal to the GH part of B, like so. And the E and F and HI don't matter because they only get multiplied by 0. So in both these cases, MA is going to be equal to pi 2 pi E 2E, and likewise MB is going to be pi 2 pi E 2E. But A is not equal to B. So yeah, this theorem is false. So this is another way that matrices do not act like numbers when you multiply them. We saw another example of this before, how AB and BA are not the same thing. even though with numbers, you do have a commutative property. Let's look at B. If AB equals 0, then either A equals 0 or B equals 0. Now, again, we're going to try to think of a counterexample, which is an example of A and B that make this false. Such that A times B is 0, so the statement applies to it, but neither A is 0 or B is 0. So A is not 0, and B is not 0. And maybe we can use the same notation from before for A and B. And if you want to pause this and try this on your own, good exercise, but I will show you my way of thinking about it here. So AB, using the row column rule, is going to be CG plus DI, EG plus FI, CH plus DJ, and EH plus FJ. And we want to make all of these equal to 0 without all the numbers being equal to 0. Now, the way I can think of to do this is just make it so CG is the opposite of DI. Maybe C and D can be 1 and -1, and G and I can be equal but positive, like let's say 2 and 2. So then when you do 1 times 2 and -1 times 2, that cancels out. And we could have the same thing happen over here. We just need the numbers here to be equal to each other, like 7 and 7. And then anything in the E and F position could also work the same way. These just need to be opposites. Or they could also be partly 0. That doesn't matter. The matrix A is still not equal to the matrix 0. So yeah, if you check this, you get AB is 2 minus 2 in the top left, 0 plus 0 in the bottom left and bottom right, and in the top right, 7 minus 7. And that is equal to the 0. So this is a counterexample, and we have shown why the statement is false. So this is yet another way that matrices do not behave like you might like them to, like the way numbers behave. Now, fortunately, matrix multiplication does behave in some nice ways. We still have an associative rule, right? You can move these parentheses around here. You get the same thing. That's the one we're going to prove right now. The identity matrix, remember, the identity matrix has 1s in the main diagonal and 0s everywhere else. So that behaves kind of like the number 1 when you multiply it by another matrix. Like multiplying the right size identity matrix by A gives you A, whether you do it on the left or on the right. You also have left multiplication distributive rules, right multiplication distributive rules, and an associative rule with scalar multiplication. So let's prove number 1 here. There's actually a really easy way to show why these are equal. Let's write C, whatever matrix C is, as columns with little c1, little c2, yada yada yada, up to little cn. Then when you do A times the product BC, the definition of BC is the matrix that has columns that are each B times the corresponding column of C. Now we're multiplying A by another matrix that has these columns. So the definition of multiplying A by another matrix is the same idea. We're going to do A times each one of these columns. And then at this point, we can just move the parentheses around, like so. And the reason for that is based on the discussion before the definition, the fact that this definition makes it so multiplying A times the quantity bx is the same thing as AB times x. It's just that now, instead of x, we have the columns of C, but yeah. And this now is the definition of the matrix A times B multiplied by a matrix that has these columns, which is, of course, just C. So yeah, this associative property works because it works for each of the columns of C, which is what we made up this definition to do. All right, in the next video, we'll talk about transposes.